Let's go to Code Milkers. We're looking at Maximal Square today. Obviously, this is a day late. I did submit it on time. I just didn't have time to record the video yesterday. So I'll go over the solution today. And then the next video will be first unique number, and I'll record that today also. So given a 2D binary matrix, so that's an array with subarrays, filled with zeros and ones, find the largest square containing only ones and return its area. So we're looking for a square so that is width is equal to height. So like some options would be 1 is a square, 4 is a square, 9 is a square, 16 is a square. You get the idea. Then we return its area. So the number of ones you find in the square shape, that's how many you return. So if we look at this example, it's pretty obvious. The first square we find is 1. Let's go across this left to right to keep it simple. So we'll go the first row, then we'll just go down from there. So we have our first square, it's 1, that's our baseline. 0, 1, it doesn't count. 1, 0, okay, we have a 1 here. Now we look to the right of it, we have another 1. Now we have to check the row below it, and we actually have a square. So the new square is 4. And we check this one, same deal, we have another 4 here, we do not reassign. We go down to this row, 1, 1, and this 1, 0 below it don't count as a square, so it's still 4. Same deal here, okay, I'll put 4. So basically, my solution was to, for every element in the array, in the current array, so if we have, so we're starting at 1. For this one, since it is the element 1, you have to try and see if it forms a square with the rows below it. So we can tell it's a square at first, incrementing from 1. So with 1, we only need a 1. My gosh, take a shot every time I say 1. We need a 1 for it to count as a square. So the next, we want to check if the current row and the row below it have 2 ones going from left to right, because that'll give us 4. Then if we pass that, we want to see if the current row and then n rows below it, so it's going to be 2 this time since we want to get 3, if the 2 rows below it also have 3 ones from left to right. So we're basically expanding diagonally, if you can imagine that. So we start at 1 here, and we're branching into a larger square, then we're going into a larger square, and each time our column expands by 1, and our row expands by 1. So you can set up a for loop to check increasing the column and then increasing the row. And you have it, how I did it was, basically, we can always tell the result's going to be 1, even if we break out of this for loop early. So we started at 1, that'll make sense in a second. Next we have this variable pointing at the 0. This is called total. So essentially, for a given set of rows and columns, they have to add up to the current to the result plus 1 times 2, because that's the next largest square possible that we're checking for. So if we miss any ones in the rows and columns dictated by that next sized square, then it can't be a full square, so we know to return the result we had originally and not times it by itself. So basically, we're just going through and expanding the column by 1 and the row by 1 with every iteration, making the square larger. And then in the maximal square function, which is the one they give us, just going 1 row at a time, each column 1 at a time. If it's a 1, we invoke try square. and we set the maximum of either the return value, try square, or the original max value. We do that for each element, and we don't skip any, because say we have our first, this red square here, you might look and say, okay, we've already gone over elements at index 3, 3, and 2, and 2, and this 2 also. But it could be that, like we see here, this is actually part of a larger square. Like it isn't in this case, but it could be that if the array was one column longer on each row, it could be that this 1 here expanded over to another 1 and then another 1, and then it actually formed a 3 by 3 square. So I didn't find a way to nicely skip them. It might be possible. Yeah, so that's the basic solution. It's very intuitive. It follows a linear pattern. It's not linear time, because you potentially would have to go down to the bottom right of the array each time if the square was big enough with enough ones to do that. So the time complexity is definitely not linear time. I'm not sure what it is off the top of my head though. Yep. That's about it. I'll submit it here so you can see the time complexity. Let's check it out. Yeah, 68 milliseconds, and it beats 84%. I thought this was interesting because I know people, I looked at some of the comments after I submitted it, people were using some pretty sophisticated dynamic tables for this problem, and I didn't use one. But my solution is just as fast as a lot of those. So I'm going to try to refactor it and see if I can get up into the 90% of JavaScript submissions. But for right now, it's a good solution. Hope this helped. Have a good one.